Welcome. My name is Pavlína Gonçalves from the University of Zurich, and I would like to introduce to you our experiment about the effect of reviewing strategies on code review performance. Code review is a widespread practice for assuring code quality. Many reading techniques were developed to inspect code in order to identify potential defects. They should assist developers in what to look for and how to review. One of the code inspection reading techniques that are widely used also in modern code review is checklist-based reading, where developers review code with the aid of checklists of common issues. Checklists tell reviewers what to look for, but are not specific about how to review. In other words, they do not offer a strategy or a scenario to navigate and guide the reviewer on how to identify the defect. Following a defined strategy to perform development tasks proved to be an effective aid in multiple contexts, for example debugging or test-driven development. We added a strategic execution to a code review checklist and developed a checklist-based strategy. We expect guidance to have a positive impact on review effectiveness and efficiency. In theory, this effect is working through lowering cognitive load of the developer. Cognitive load refers to the extent of developers' working memory usage. Guidance makes code review more systematic and focused. This saves up the developer's working memory for the more complex parts of the review. However, the mechanism is not yet supported by data. We formulate two research questions. Does guidance in review lead to a higher review effectiveness and higher review efficiency? And is the effect of guidance on code review mediated by a lower cognitive load? Our results can have multiple implications for research and practice. We will be able to say whether further guidance in review in form of assistance with the strategic execution of a review gives an additional boost for developers' productivity and defect identification. If it is so, tool support for checklist execution could be further encouraged. This might be especially relevant for training purposes when the developer does not have so much of experience to guide his own review. Furthermore, we will test whether the hypothesized reason for a better performance with guidance can be supported with data. This might encourage investigations that do not focus only on how to make the code review productive, but also on how to lower the cognitive load so that the mental capacity of a developer is freed for the more complex parts of the review. To test our hypothesis, we designed the following experiment. The experiment is performed online by 100 developers from an Indian outsourcing company. In the core of the experiment, there are 3 review tasks. Firstly, the developers perform a short, easier review, then 2 long reviews follow. Each developer is randomly assigned to an experiment treatment and works with the same condition in all the reviews. The treatments are a review with no guidance, a static checklist, and a checklist-based reviewing strategy. The tool shows a code change to the developer and enables them to leave a remark on the line of code where they identify a potential defect. In the checklist condition, the checklist itself is displayed on the left side of the screen with an option to hide it and see the change in full. The strategy is implemented as a gradual checklist execution with features that should maximize the understanding of the code and minimize jumping through the code. The strategy iterates through the chunks and classes and offers only the checklist items relevant to the highlighted chunk. After each review, we measure the cognitive load of the developer. Cognitive load is measured by a standardized questionnaire. It measures 2 components of cognitive load, mental load and mental effort. The items are answered on a 7-point scale in range from strongly disagree to strongly agree. In other parts of the experiment, we provide tutorial for the tool, introduction to the software system, measurement of the usability of the used treatment, and we collect the sample demographics. To test the relationship between guidance and review performance, we will do a one-way ANOVA. As the post-hoc analysis, we plan to do the Takis range test. For testing whether the lower cognitive load mediates this relationship, we plan to do mediation analysis using the mediation R package. Our study faces multiple validity threats. We conduct the experiment with a sample of developers from an Indian outsourcing company. Even though it gives us some advantages like a control over the dropout of participants, all of our developers are from a single company and a very similar socio-cultural background. This can introduce bias in the experiment. Another issue is related to the implementation of the checklist and strategy as we created our own. We base ourselves on the best practices and principles we identified in the literature. However, this is still only one example and implementation of these conditions. Therefore, our study faces the mono-operation bias. Similarly, we can be limited with the possibility to generalize our results to other changes and types of defects. Thank you for your attention.